Hello everyone, Mr. Fawcett back again with another AP Calc AB lesson. Today we're going to touch on an important theorem in calculus, one that you'll use pretty consistently, and that is the intermediate value theorem. Now, before we just go into what the theorem states, I want to throw a little visual at you and hopefully start a little internal dialogue and discussion, kind of get those creative juices flowing before we jump into any problems. So, here's a set of axes, and I'm going to put 2 points on the graph. I'm going to put one at, it doesn't matter what the x value is. Let's just say it's -5, y value is -4. And I'm going to plot another point up here at 9 and 3. So my question to you, if you knew that this function was continuous on the interval -5 to 9, on the closed interval -5 to 9, so I'll give you these conditions. So continuous on -5 to 9, is there going to be a point on the function where the y value is equal to 1? So, is there an x value on -5 to 9 such that y is equal to +1? So, would we be able to be certain that there is an x value where the y value is going to be 1, or where there isn't an x value where the y is going to be 1? And maybe you just want to pause the video and sketch out some possible graphs of what would work. Okay, so maybe you've sketched some graphs and tried to answer this question. So number one, or the only condition rather, is that the function is continuous. So there's an example of a continuous function. Now, is there going to be a point on that function or on that graph where the y value is equal to 1? So the y value is going to be around here somewhere. So does the function ever intersect this horizontal line? And we see that it does. It's going to intersect right here. So there is going to be a point where the y value equals 1. Now the problem is, this isn't the only type of function that I could have, right? There's an infinite number. So maybe let's draw another one. I'll leave y equals 1 up there. So now that I've left y equals 1 up there, is there a way for me to not intersect that line as I trace the function from -5 to 9? So let's see. Maybe I can come over here. Oh, I'm still going to have to cross the line before I get to 9, so that doesn't work. Let's see, what if hate when I forget to change out of my eraser. That's okay, there we go. Got to get that point back on the graph though. Okay. What about this? So I've certainly bypassed that horizontal line y equals 1. So would this be a counterexample? Would this show that I don't have to have a point where the y value is 1? And it's not a counterexample because it doesn't fit the condition I gave you, right? It doesn't fit the continuous on the closed interval -5 to 9. We have a jump discontinuity. So this is what the intermediate value theorem essentially is talking about. We're going to get to a formal definition in a second, but essentially if you have a continuous function and you know what the two y values of the endpoints are, well, you know that the function's going to touch every y value between those two y values, right? So our two y values are 3 and -4. So no matter how I draw this function, right, no matter what function I choose, again, I keep choosing the eraser, and I chose it again. That's okay, we'll get it. All right, here we go. So no matter what path I choose for the function to go, it's going to have to take on every single y value between -4 and 3. And that's essentially what the intermediate value theorem states, but let's put a formal definition down in the box below. So per usual, I wrote down the theorem to save some time. And I also put a visual diagram down below. Now the diagram's not completely filled in. It's just a template for what we're going to use when we discuss the theorem. What I would do if I were you, I would pause the video. I would copy down a theorem. I might reread it a couple times. And then I would see if I could understand the theorem using the diagram below. So maybe you need to draw some other things in the diagram to kind of experiment with what the theorem is saying. But I think it's going to help you bridge the gaps that may be caused from just reading the theorem and looking at the symbols and the intervals that are in it. So take a few minutes, see if you can try to understand what the theorem's saying on your own, and then we'll give it a good discussion. Okay, so the theorem says, given f of x is continuous on the closed interval a to b, and L, which is just a real number, is between f of a and f of b, then there exists a c on the open interval a to b such that f of c is equal to L. So again, that's a lot. Let's jump down to the diagram and see if we can turn this into a visual diagram. So first thing is f of x must be continuous on the closed interval a to b. So when I draw this function, we know it has to be continuous. Second condition is that L has to be between f of a and f of b. So if I kind of sketch out where these f of a and f of b points are, okay, I just had to choose an L that's between them. It can be any number between those two y values. I just chose one that was positive here. Now, if I draw a function, we'll put that in blue. So I'm just going to draw a function that looks like this. It is guaranteed to hit that y value of L. Okay, and the x value for when it hits that y value is going to be between a and b as well. So the L value is between f of a and f of b, and c will be between a and b. Okay, and this point, we could actually write it two ways. We could say c comma f of c, or c comma L. And that just has to do with what's up here, right? We said f of c would be equal to L. So if we have a y value in between the two y values of the endpoints, then not only will the function hit that y value on the interval, but the x value for that point will be on the open interval. Okay? Let's go down and talk about what's important from this theorem, what we need to really focus on. Okay, so number one says, what are the initial conditions for us to be able to apply the theorem? So we said there was two things that had to be true before we went even further. Again, you may want to look back at the theorem now, pause the video, and come up with what those two things are. The first thing is f of x is continuous on the closed interval a to b. It must be a closed interval. It cannot be an open interval. Second thing is that L is between f of a and f of b. Okay, L is not between a and b, it's between the two y values, because L itself is a y value. So if those two things are true, well, then the conclusion of the theorem says there exists. This theorem doesn't tell us where the c value is, it just tells us it exists. there exists a C on the open interval a to b such that f of c is equal to L. So we're going to talk about a lot of theorems throughout this course, and it's always important to identify what the initial conditions are and what the conclusion is. What has to be true for us to apply the theorem? Those are the conditions, and then if those conditions are true, what follows? Okay, let's look at a little informal proof. I spaced these notes out in my video so that we would have more space, but they may not look like they do on your paper. That's okay. And we've kind of already done this, but it's, again, it doesn't hurt to get more practice to really understand this theorem. It says, suppose you need to draw a function f of x over the interval, closed interval 0 to 8. You are told that f of x is continuous. You also know that f of 0 equals 9. So right away I'm going to mark that. F of 0 equals 9. And f of 8 is equal to 2. And the function's continuous between these 2 points. So it says suppose our L is 4. So our L is right here. That's the line we are guaranteeing the function to cross. And is it possible to draw a function that meets the conditions above without crossing the line y equals 4? And again, I asked you this question in the beginning. There is no way to do that unless you do some sort of jump discontinuity, right? But then the function's not continuous, so that isn't allowed. If you make sure the function's continuous, there is no way to go from blue point to blue point without crossing that pink line, which represents that y value. Okay. All right, let's do one set of practice problems, and then we're going to call it for the first half of this video. And then we will come back for part 2 with some more practice problems. So again, I'm just trying to space these problems out in the video so we have plenty of room. Can even go smaller. Okay, so we have a piecewise function here, f of x, which is graphed below, and we have 4 questions that we are going to work through. We're going to label them 1, 2, 3, and 4. 1 and 2 go together, and 3 and 4 go together, so that's why I'm using different colors. So let's look at number 1. It says, is there a value of c on the open interval -5 to 2 such that f of c is equal to -1? If so, what is that value of c? So let's look at that open interval, -5 to 2. And does the function ever hit -1 as far as a y value goes over that interval? And we see that it does right here. And that point would be 0, -1. So yes, when c equals 0. Now question 2 is a little different. It says, does the IVT guarantee a value of c such that f of c is equal to -1 over the open interval -5 to 2? So we know that there is a value, right? Because we said that in number 1. We found the value. Number 2 says, does the IVT guarantee that there was a value? Now, those are 2 different things. Quick real-world example. I could put $20 on the floor underneath your desk, and then before you walked in the room, I could say, I guarantee that you're going to find $20 underneath your desk, right? However, just because I don't guarantee it, so 99% of the time, I'm not going to say that to you as you walk in the room. But it's possible that you would still find $20, right? It could still fall out of someone's pocket and be underneath your desk. So something doesn't have to be guaranteed for it to occur, which is what could be going on here. So just because it happens doesn't mean that the IVT guaranteed it. We still have to use the theorem to justify. So when we're going to use the IVT, we have to look at the initial conditions. So the first one was, if we look back to the previous page, is the function continuous over the closed interval? So as we trace this interval, which is our very basic form of saying whether something's continuous or not, we see that there's this jump discontinuity here at -2. So because the function is not continuous, the IVT cannot be used. So no, f of x is not continuous on the closed interval -5 to 2. And you don't have to go any further. If you wanted, you could also say it's discontinuous, or you could say, let's be even more specific. We'll say jump discontinuity at x equals -2. But you don't have to go that far. You can just merely say that f of x is not continuous on the closed interval, thus the IVT cannot be used. Let's look at number 3. It says, is there a value of c on the open interval -5 to 2 such that f of c is equal to 4? And then what is that value of c? So if we come up here, this time we're only at -5 to -2, not to +2. So careful there. So -5 to -2. However, we still see that the function reaches that y value of 4. So at -3, that's the x value at which the function is equal to +4. So yes, when c equals -3. So again, part 4 asks us to guarantee that using the IVT. So does the IVT guarantee a value of c such that f of c equals 4 over the open interval -5 to -2? Why or why not? So let's first check the initial conditions. Is the function continuous from -5 to -2, closed interval? Well, we can clearly see that it is, so that checks out. Now the second initial condition is that y value we're looking for? Right, so f of c, that L value, that f of c value, which is that y value, is that between f of a, so we have this interval -5 to 2, which is our open interval a to b. So f of a, if we look at the graph, f of a is equal to 0, f of b is equal to, -5 to -2. Is equal to 3. So basically, this down here, this f of c value, this L value, has to be between 0 and 3. And 4 is clearly not between 0 and 3, so it fails the second initial condition. So we could say no, because 4 is not between f of -5 and f of -2. And you do need to show what f of -5 and f of -2 are. Okay, that's going to let the AP reader know that you actually understand that 4 is not between those values and you're not just making a random guess. Okay. So in both of these scenarios, the IVT was unable to be used because the initial conditions failed. And I'm doing this problem because I really want to hammer home that point. You have to check the initial conditions before you invoke a theorem. For the IVT, there's 2. The function must be continuous over the closed interval, and the y value must be between the 2 y values from the endpoints, right? It would have to be between these 2 y values right here, but you can see that it falls outside of those y values. So we can't use the IVT to say that the function has to touch that point. It can, and we see that it does, but it doesn't mean that the function has to. Okay, we are going to stop here, I believe. And when we come back next time, we're just going to be working on these practice problems. Again, looking to see if the IVT is applicable by seeing whether it fits those initial conditions. So I look forward to seeing you next time. Until then, enjoy the rest of your day.